This is an extract from a conversation I had with Professor Ifan Hughes in 2016. Ifan is based at the Centre for Atomic and Molecular Physics at Durham University, where he and his team are carrying out world-leading research in cold atomic physics. Whilst we were talking, Ifan showed me slides from various presentations as a way of introducing me to his field, but we also covered more general areas, such as the idea of collective intelligence in scientific research, which I'm particularly interested in, as well as talking about the properties of the scientific imagination. There were also some fascinating insights into the politics of sharing knowledge, as Ifan described his team's collaboration with Armenian scientists who manufacture cells thinner than the wavelength of light. A team Ifan rather romantically described as being based in the shadow of Mount Ararat. What struck me most forcibly, though, and this edited version of the conversation focuses on this, was when Ifan speaks about particular spectroscopy graphs, because these become a springboard for him to talk not just about the detail of his work, but about his fundamental approach to teaching and research. Embedded within these graphs is the close relationship between prediction and experimental outcome, which signals why Ifan and his team are world leaders in their field. But at the end of this edited version of the conversation, he speculates on the possibility of sharing experimental results to his scientific community in a different way, a reverse question, as he calls it. Before this, though, Ifan spoke to me about that idea of elegance, the term often referred to in mathematics and fundamental science, being manifest in one of the data graphs he's showing me. But we begin here by looking at a spectroscopy graph that Ifan describes as one of the highlights of his career. So, going back to this, you said this was a highlight of your career.
I would actually, yes,
Yeah.
I would. That's one of the things I'm most proud of. There are three traces there. One was taken at room temperature, one was taken at about 35 centigrade, and maybe one at 40 centigrade. When you heat the metal in the bottom of the box, the atoms evaporate, so you get more atoms, which means, so this is room temperature, that's a bit hotter, that's even hotter, because there are more atoms, they absorb more of the light, so less light goes through. There are in fact 6 traces on that screen, so depending on how good your eyes are. So for each one of those red data traces, there's actually a dotted black theory. So when we're not in the lab, we write down on bits of paper what we think should happen. We then get a computer to calculate lots of maths. And our idea of fun is to predict what should happen, go to the lab and measure it, and then the big discipline is to not just say, oh, they look the same, it's to actually plot them on top of each other.
Right. So, in other areas where you've got the theorists and the phenomenologists and the experimentalists,
we do both. We do in-house
there?
theory and we do the experiments.
Right.
And occasionally the theory is just a bit too hard. But then we tend to deliberately concentrate on doing experiments where we know we can also do the theory. And what we're aiming for are traces, graphs, some kind of visualization where it is obvious by looking at it. So what we've done here is multiply the difference between the red and the black by about 100 just to see that it's there. So that's a clever visual way of showing that they agree phenomenally well.
Right.
So our figure of merit is this one, basically. How large do we have to multiply the difference just to see it?
Right.
Because if you didn't have a good theory, you'd get some red lines here and the black ones over there. It would be hopeless. So somehow we're now victims of our own success because our red and black is so good. Most people think there's only 3 traces. There are in fact 6.
Right.
And it's the fantastically exquisite precision of the experiment, meaning the lineup is nearly exact.
Okay, so that's the significance
That's
of
the
this.
significance.
Is that relationship between the projected
and
the actual
reality.
Reality in inverted commas.
Yes. Yeah.
He's doing inverted commas.
Actual is I prefer.
Right. So when did you do that?
It started. The first publication was in 2008, and we've built on it since. And we only published our computer code to explain how and why this happened last year, actually, 2015. But it's been about a 15-year project that's culminated in, now that we've got this basis of understanding of atom-light interaction, we're now branching off and doing a whole host of fantastic other things, actually.
So what is this called?
So I would, it's actually called, spectroscopy is the idea that you understand how light interacts with matter. And it's atomic spectroscopy. We deliberately choose some of the metals we put into our vacuum are simple.
Right.
Deliberately. Otherwise, we wouldn't be able to calculate what should happen.
Right.
And it turns out there's enough to do with some simple atoms, a box, some light and a magnet. That's actually probably going to be my career. That's sufficiently rich because there are lumps and bumps. In a minute they're going to move around.
And that talks of the universe.
It does, yeah. We can use that to, so this concept of, so if you pick up a textbook on astrophysics, it will tell you about types of stars, what's in each star.
Yeah.
How do we know? No one's been to any of these stars. No one's actually put a probe inside a star. The only reason we know that is a very, very powerful point. It's just, in inverted commas, looking at things like lumps and bumps and dips, how wide they are, how tall they are they in the right place?
Right. My final question. Going back to the set of graphs that you had that had the rotational lights that produced the green cat's ears.
At one stage, we were thinking of having that made as a giant poster, just because the visual. So it's false colour. Our laser actually, this is a graph from a computer. It could just be black on white. We chose to kind of colour it, and all it is a sequence of, here's the cell, we just record how much light comes through. At room temperature, hardly any light comes through, and then we just set the heater going. When it gets to 130 centigrade, something more interesting happens, and when it gets to 330 centigrade, it actually turns into that. But there's somehow this, for us, beautiful sequence where these four things, they change their shape, and then then the four disappear into two, and then eventually the two merge, and you get one broad thing.
Yeah.
And that for us is actually somehow beauty in science.
Yeah. Do you know Bridget Riley's work?
Not really, no.
She's an op artist, you know, those group of artists that work with sort of optical phenomena.
Ah, right, okay.
But it's interesting because it looks very similar to that. Yeah. But it's what it means to you, isn't it?
Exactly. It's not. I mean, even if you have even other scientists who have if we took the axes off, you know, there's something visually attractive. But for us, it's so much more powerful because we also know that this was the sequence of curves that allowed us to get some of the highest impact research papers we've ever published in Durham also came out of that.
Right.
So it isn't just and it's pretty.
Yeah.
It's pretty, and it's actually there's some scientific elegance is the thing we're actually.
Yeah, because that word elegance gets used a lot, doesn't it, in science, and so it's interesting to have a sort of visual manifestation. Of something
that's it for us. That's some of the culmination of the process. Is.
So. My question was about the graphs that you had. So when
really
you were talking about this reverse question. Yeah. Have you done that?
No, I haven't.
Why not?
There's two answers to that. I mean, the first one is at some level I'm slightly scared, to be honest. The second one is I'm going to say is in a more positive light. When I give seminars, I'd like to think of myself as a good educator as well. This is slide 15 or something in. I've actually set up the whole story. So I tell people what's going to happen. I tell them about atoms, then I tell them about the rotation, then I tell them about the magnet, then I show the simple spectra, then we slowly build it up. So I would like to think if I've done my job well in the seminar, that when I kind of this is unexpected, but in the context of what I've been speaking about for half an hour, most people in the room maybe aren't that surprised. So probably the way I'd have to do it is literally right at the start of the seminar, just turn it into and by the way, today at some stage, this is going to happen. What is it? Maybe I'll do that the next seminar I give.
Maybe you need to give them the heads up before they come, so they had time to think about it.
You don't want to give people time to think.
But why are you scared?
No, I'm not actually. No, well, the fact that I mentioned it to you means clearly I have thought about it. It's just what I haven't done it before. I think the more I think about it, yes, I think I would. Well, it would be fascinating.
Yeah.
It would be genuinely fascinating to see. My expectation is, without the context, people wouldn't have a clue.
Right.
But I haven't done it, so.
But would just that as a methodology, would that be seen as kind of wrong-footing people, or
it would be seen as interesting,
right.
as in maverick. Yeah.
Yeah.
But it's this. It's not a trade-off. If your whole talk was, well, this is unexpected, and maybe I don't know.
Yeah.
The audience would, well, all right, well, come back when you do.
Yeah.
So that somehow, as a corollary to that, we then tend our idea of clarity and nice scientific papers is by explaining carefully what we've done, having the simple case first, showing that it works, and then bolting on the complexity, culminating in the fantastic stuff at the end. So I guess because I teach heavily, I think of my research seminars as also a teaching at some level. So I'm conditioned to not go with, well, that's a mystery.